Okay, we're going to finish up with the central auditory nervous system. Again, we're not going to go into immense depth with the central auditory nervous system, but there are a few structures that are important to know their function. And so, um, let me go back here. I think I skipped something. So here are some of the structures: cochlear nucleus, superior olivary complex, lateral lemniscus, inferior colliculus, and the auditory cortex is the other structure that's quite important. The brainstem is the lowest portion of the brain, located just above the spinal cord. Okay, and a lot of these structures are at the level of the brainstem, and then some at the levels that are a little higher, and we'll see that. And so, one thing about the auditory system is that there's a lot of what we call redundancy in the auditory pathways, and throughout the whole neural system within the body. There's a lot of redundancy, meaning information will often travel in an ipsilateral route, meaning on the same side of the body, but also a contralateral route. In the auditory system, most of the heavy fiber tracks are contralateral in nature. So when you hear something in your right ear, most of that information is going to be processed in the left auditory cortex and vice versa. Okay. The point at which you see crossings is decussation is the word, and I'm sure you know that word from your anatomy class. And so the complexity in the auditory system increases a lot from the auditory nerve to the brainstem and then to the cerebral cortex. And I always use the analogy that, our brain at the level of the medulla and the pons and those lower levels have a very basic rudimentary function, respiration, and those types of things. But as you go up to the midbrain and subcortical levels and then the cortex, that's where all the abstract processing, our ability to think, reason, talk, that kind of thing, those are cortical. That doesn't happen in the brainstem. That happens in the cortical areas of the brain. Okay, we have tonotopic organization that's preserved from the cochlea, the basilar membrane, all the way up to the auditory cortex. Okay, so that frequency organization is preserved throughout the entire system. Okay, so the auditory brainstem. This is where the auditory nerve fibers basically hit the first part of the central system at the level of the medulla and the pons. Sometimes here referred to as the cerebellopontine angle, where kind of the cerebellum and the pons are close to each other. So again, some pathways are ipsilateral and some are contralateral. That's basically what this says. So let me get my little handy dandy highlighter here. So you will have some pathways that course ipsilaterally, but the stronger pathways will course contralaterally. Okay. So ipsilateral is when that's on the same side, and then contralateral. So here you have the cochlea, right? We were talking about the hair cells, then the auditory nerve, cochlear nucleus here, superior olivary complex in this middle. Actually, it's more there. Well, let me erase that. It's all of this right here. The superior olivary complex is really important, and we'll talk about it, but it's the first structure that gets input from both sides. And so it does a lot of complex things. Okay. Then the midbrain, you can see, and then, the cerebral cortex, right? That's all gray stuff. It's blue here, but it's all gray. And this is where the final kind of station for processing occurs. Okay, the auditory cortex is here on each side. It's in the temporal lobe, right? Oh, better at that than I thought. Temporal lobe. But yeah, this is the auditory system, and we'll go over a little bit. Let's see here. Hold on one second. Okay. Let me make sure I'm in the right place. I think I hit the button too much. So the pons. So here, if you look down here, this is the brainstem here. It's these three areas: the medulla, the pons, and then the midbrain. Okay, midbrain's getting closer to the subcortical areas, right? So that does a little more finite processing. But the auditory nerve fibers enter the central nervous system in this region, the medulla pons area. And so cochlear nucleus, just the first stage. Don't worry about all those details on there. But the next stage, the next station, the superior olivary complex, or the SOC, is quite important. The SOC is in the pons. Oops, I'm sorry. Is in the SOC is located in the pons region. Okay, it basically is the first central auditory station that gets input from the right ear and the left ear and kind of meshes it together. Doing so provides I can't find my cursor, provides for the information to help us with localization or lateralization. And localization, as we talked about, is determining where a sound is in space. Lateralization, if it's coming from the right or left, and that's usually done through headphones. Localization is done just in the field, in the sound field. Like I always say, if we were in class, I would be moving around the classroom, having you close your eyes, trying to determine where I'm at, but we're not in a class, so we can't do that. Okay. So again, the SOC, mentioned it was right here. Takes input from both sides. So the medulla, the cerebellum, okay, and then the midbrain are structures within the central system that you should be familiar with. The cerebellum, it's at the pons, involved in heavily involved in balance, the coordination of movement, but there's also a lot of literature which doesn't get cited a lot that implicates the cerebellum in processes that involve auditory function and other kind of cognitive functions. Then you have the midbrain, which is more rostral, closer to the cortex. And again, here's the visual for you. If you remember, spinal column, medulla, pons, midbrain, and then you have the thalamus. I always tell students and use this terminology. The thalamus is essentially a gateway for sensory processing to the cortical regions. That's what the thalamus does. It's like this relay station for sensory processing to the cortex. All right. Again, we talked about the midbrain. We don't need to go over that again. The thalamus, okay. The pathways are designed for fast and effective delivery of critical neural information. Okay. From an auditory standpoint, it's just closest to it. The medial geniculate body is the MGB, or medial geniculate body, is the auditory system structure at the level of the thalamus, but that's not that important. The cerebral cortex obviously is an important structure to talk about. The auditory cortex, right? Very important for speech perception, communication. It doesn't, in and of itself, allow you to understand speech because it has to kind of interact with the language processing center. but at a basic level it does. Within the cerebrum, it's the highest level of the central auditory nervous system. And there's a temporal lobe on each side, right? We talked about the temporal lobe. Information from the thalamus reaches the auditory cortex via what we call thalamocortical pathways. Okay, and again, it's just the sensory processing structure, gateway, if you will. All information reaching the cerebrum from lower pathways and centers arrives first in the primary auditory cortex at Heschl's gyrus. So Heschl's gyrus is the primary auditory cortical region. There's some other auditory cortical or secondary regions, but Heschl's gyrus is the primary auditory cortical region. The planum temporale, some people say planum temporale. I'm not sure which one's right, but I've always taught the planum temporale. Is located immediately or posterior to Heschl's gyrus and plays a huge role in language processing. Okay, the planum temporale is larger in like 70% of people on the left side, showing a strong kind of dominance for language processing. Okay, but again, the planum temporale is very close to Wernicke's area, very close to the auditory cortex, and so very important in language function. So it's somewhere, I don't know if it's labeled here, primary auditory cortex, Wernicke's area is here, planum temporale is right there. I mean, they're all right next to each other for obvious reasons. There you have Broca's area, right, for production, speech production. You should know most of these structures. We talked about efferent versus afferent. One of the strongest efferent fiber tracts is the olivocochlear bundle. The superior olivary complex, right? It's part of that, the OCB. Basically, information from higher levels in the central system is information is sent down to the SOC, and then there are tracks that go from the SOC down to the cochlea. Okay, so you have this efferent type of information going from the brain to the SOC, and some going from the SOC to the outer hair cells. I do believe there's some tracks going from like the cortex, the brain, down to the outer hair cells, but you get the point. It's efferent activity and may help improve the detection, localization, and perception of speech when there's background noise, and may also be related to auditory disorders like tinnitus, people who are exposed to loud noises. Now, the vestibular system, again, this is something we don't spend a lot of time on. Dr. Callahan or whoever you had for anatomy and physiology may have. But again, it's basically for detecting, coding, and processing movement, the vestibular system. Vertigo is a true sensation, and we'll talk about this when we talk about case history and things. Vertigo is a true sensation of movement when there actually is no movement. It's not lightheadedness, but it's a prime feature of a vestibular disorder. So let's look at the vestibular structures. Semicircular canals, there's 3 of them at different angles to help when you turn your head different ways. Okay, those are the primary structures for balance. And then you have the vestibular nerves that takes the information from those to the brain. Okay, the vestibular ocular reflex, when you move your head quickly, your eyes will stay put on something. That's basically the reflex of the vestibular system saying, hey, we're moving our head, but our eyes are going to stay still. And people who have dizzy problems often have an impaired vestibular ocular reflex. Okay, so that's it, and I'll see you in class.